Welcome to the online video lecture series for intermediate algebra at Wayland Baptist University. My name is Dr. Scott Franklin and I'll be leading these videos. This video is for section 1 of chapter 1, where we will begin laying a basic foundation for intermediate algebra. We're going to be talking in this section about algebraic expressions and real numbers. In this course, you're going to be learning a lot of basic skills in algebra to prepare you for our college algebra course at Wayland. The goal of algebra as a whole is basically to find the missing piece. We are going to study how to model the real world events, real world phenomena with variables and mathematical operations, and eventually set up equations that help us to predict what's going to happen in the real world, whether we're talking in biology, physics, chemistry, and other sciences, or finance, or any area that works with quantitative data, that is, numerical values. And the relationships between the quantities in the real world will be represented by these equations. And in general, we're going to want to study how we find the missing value. If we have a set of information provided to us and we know the relationships between the unknown quantities and the known quantities, can we find the values of the unknown quantities? That's what algebra is all about. So to lay the foundation, we need to first talk about what we mean by algebraic expressions. We're going to discuss real numbers, what they are, and how we perform operations on those real numbers in this chapter. So let's go ahead and get started. In this section, we're going to cover the following essential concepts. We're going to learn to translate English phrases into algebraic expressions, evaluate algebraic expressions, use mathematical models, recognize sets that make up real numbers, use set builder notation, using the symbols the element and not an element of, and use inequality symbols. Open your lecture notebooks to page 1 and we will begin by talking about algebraic expressions. Now, if a letter is used to represent various numbers, that letter is called a variable. So for example, in a particular problem, x may represent any type of numerical value. For example, it could be, say the number of minutes you can stay in the sun. Say whenever you're sunbathing or whatever. Okay, so that might be x. Turns out, if you let that be x, then if you use sunscreen, then the value 6x might be the amount of time you can stay in the sun when you use a particular type of sunscreen, 6 times as long, right? X can be used to represent any number of quantities. Can be representing height in a problem, weight, cost of some particular object, anything that has a numerical value. Now, a combination of variables using addition, subtraction, multiplication, or division, powers, or roots, those are all called algebraic expressions. For example, the expression x plus 6 is an algebraic expression. It's got variables, it's got the addition sign, and it means any number added to 6. X minus 6 would be another algebraic expression, meaning take 6 away from x. 6x is an algebraic expression. X divided by 6 is an algebraic expression. You can have combinations of these. You can have multiplication and addition in the same algebraic expression, 3x plus 5. You can have exponents or powers showing up. We'll talk a little bit more about what exponents mean. Or the square root of, say, x, all added to 7. Those are all examples of algebraic expressions. Now, in some special circumstances, we may use a letter to represent a single but unchanging value. In that case, it is called a constant. For example, if I were to let d be the number of days in a year, that doesn't change throughout the problem. or throughout any problem, right? That's a fixed value, but sometimes it is easier to represent a quantity by some letter than it is to plug in that numerical value over and over again. And you'll see throughout the semester that throughout this course, that we use a lot of symbolic notation to help simplify or shorthand the type of operations that we're talking about, the mathematics that we're talking about. We use a lot of notation. Now let's talk about how we can take standard English phrases and convert them into algebraic expressions. Now, whenever we explain a problem that involves mathematics, we will use certain English words to describe certain mathematical operations. For example, if we're talking about addition, we may use words like sum or plus, increased by, or more than. For subtraction, we used phrases like the difference between two numbers, or just minus. Or we can also talk about some number decreased by some amount, or some amount less than another number. Multiplication, some of the terms that we most commonly use for multiplication are product, times, of, like 1/2 of something. It's commonly used with fractions, or twice, or thrice, 3 times something. Those are types of expressions in English that have a mathematical operation of multiplication attached to them. Division, we use words like quotient, divide, per, and ratio. So you're going to get some practice through the homework that you'll be doing in this section of translating these phrases into algebraic expressions. Let's do a couple of examples here. If I were to say, let's write 9 less than 6 times a number as an algebraic expression. Let's let x be the number. How do we do that? Well, let's start with what's closest to the number. 6 times a number would be 6x. Okay? Notice how I'm going from where the phrase number is, 6 times that. Now, how do we take 9 less than that? Now, even though less than is subtraction, I'm not going to say 9 minus 6, because less than means to take that 9 away from some value. I'm going to take 9 away from 6, so it's 6x minus 9. This word than sometimes is tricky. Just remember that in general, it means in the opposite order. Right, that we're going to take 6 times the number less 9, or 9 less than that number, which would be 6x minus 9. That's how we write the algebraic expression. Now, if I were to say, let's write the quotient of 5 and a number increased by twice the number. All right, let's start with the first phrase. Quotient of 5 and a number. Quotient is division, so that means 5 divided by the number, which I'm using x to represent. Increased by would be an addition, so I'm going to add that value. Twice the number would be 2x, so 5 over x plus 2x is the algebraic way of writing the quotient of 5 and a number increased by twice the number. Once we have our algebraic expressions, one of the things that we want to be able to do is to evaluate them for certain values of the variable. Now, evaluating an algebraic expression means to find the value of the entire expression for a given value of the variable. So, for example, consider that we have the expression 81 minus 0.6x. And that expression represents an approximation of the percentage of American adults who smoked cigarettes X years after 1900. Evaluate the expression for 1950, or x equals 50. Now, one of the important things that you want to always do on any word problem, and you're going to see several of them throughout every section, is to make sure you understand what the problem is saying. The value of this expression is this percentage of adults who smoke cigarettes. X represents the number of years since 1900. So if I'm asked to find the value at x equals 50, I'm actually being asked to find what percentage of American adults smoked in 1950. Now, in order to evaluate an expression, what I always suggest that you do is take the original algebraic expression, just write it down, and everywhere there is a variable, replace that variable with parentheses. Just open up the parentheses, okay? 81 minus 0.6, and then stick in here the number that you're plugging in for that variable. So we're plugging in for that variable. So I'm going to stick 50 right there. Now when you see two numbers adjacent to each other or a number sitting next to parentheses, that implies multiplication. So to evaluate this, I'll have to multiply 0.6 times 50, which...
So if you take 0.6 times 50 is 30. Now you can pull out your scientific calculator for this, which is a required resource for this class. But if you multiply that out either by hand or by scientific calculator, you should get 30. Because if you take 0.6 times 50, remember that you multiply, when you multiply by 10, you move the decimal place 1 to the right, so you get 6 times 5 is the same thing as 0.6 times 50. So anyway, that's 30. So you have 81 minus 30, which gives me 51. By the way, on this line right here, notice that I did the multiplication first and then the subtraction, and that's something that we refer to as the order of operations. We'll get to a little bit later. Now, I will point out at this point we got 51. We need to interpret that back into the context of the problem. What does this 51 mean? Well, it was the approximate percentage of American adults who smoked cigarettes X years after 1900. So this would be 50 years after 1900. So in 1950, we would approximate 51% of American adults smoked in 1951. That's an approximation using...
As we mentioned earlier, one of the elements or operations involved in algebraic expressions is powers or exponents. So let's just make sure that everybody at this point knows what is meant by an exponent. That is whenever we see a number, say b, or as you see down here, the number 3, with a little superscript, a number up raised above, sitting to the right and up. That is called an exponent, that number that's up there. So this is the exponent right there. And whenever you see a number to a whole number, or even I should say a counting number, 1, 2, 3, and so on, what that means is you multiply b times itself, and that number of factors is n. So down here, when you see b to the nth power as 3 to the 4th power, that means 3 times 3 times 3 times 3, which we can evaluate pretty easily by just doing it one step at a time. So start with the first two. 3 times 3 is 9. That's what we get with these two, right? Times 3 times 3, so take 9 times 3, we get 27. Times one more 3 is left over, right? So 27 times 3 is 81. 3 to the 4th power is 81. So we've got to make sure that whenever we see an expression that has several operations involved, whether it's addition, subtraction, multiplication, division, powers, or roots, that we know what order to perform those operations in. Because clearly, if I do 3 minus 2 times, say, 4, I'll get different answers if I do the subtraction first and then the multiplication than if I do the multiplication first and then the subtraction. Right? If I do the minus first, I would get 3 minus 2, which is 1, times 4, which is 4. If I did the multiplication first, I have 3 minus 8, and 3 minus 8, as we'll discuss later, turns out to be a negative 5. But you get two different answers, right? So they're not necessarily the same thing. So we have to make sure that everybody that looks at 3 minus 2 times 4 can get the same answer. Okay, so what we're going to decide ahead of time is that there is going to be an order that we must do our operations in, and that order makes it so that everybody gets the same answer every time. Okay, so here's our order. First, perform all the operations within the parentheses. Okay, the parentheses symbols. Next, evaluate all exponential or exponent expressions. Next, do all multiplication and division. in the order in which they occur, working from left to right. Finally, do all addition and subtraction in order in which they occur, working from left to right. Now, instead of having to memorize it in this form, there is a helpful mnemonic that you can use. It's this phrase PEMDAS. Okay, the way that I remember it is, please excuse my dear Aunt Sally. PEMDAS. Okay, now the P will stand for parentheses. The E stands for exponents. What you got to remember here is you do the next two together. Multiplication and division is the MD, and addition subtraction is the AS. Okay, so first we do parentheses, then we do exponents, then we do multiplication and division, then we do addition and subtraction. Okay, so consider the following example. Let me go ahead and write it in. Let's do the following. 7 plus 5 times x minus 4 cubed for x is equal to 6. Okay, remember the rule is to plug in for x, so we're going to take 7 plus 5. I'm going to replace x with 6 minus 4 cubed. Remember, my practice is to always turn all my variables into parentheses and then stick the number inside. Okay, so now let's go through our order of operations. PEMDAS, please, parentheses. I can't do anything on the innermost parentheses, and we always start from the innermost and work our way out. Innermost parentheses, 6, there's nothing there, so next I do 6 minus 4. Okay, 7 plus, and then 6 minus 4 is 2 cubed. So we worked inside the parentheses. Next, we do exponents. So 2 cubed would be next. So 7 plus 5. Now what's 2 cubed? It's 8. 2 times 2 times 2 is 8. And there's an understood multiplication when you see numbers sitting side by side or next to parentheses. Okay? What's next? Next is multiplication and division. So from left to right we do multiplication. Here's the multiplication, so we do it. We'll have 7 plus 5 times 8 is 40. Now we do our addition and we get 47. That is the value of that expression for x equals 6. So can you tell me now, back up here on this one, which one is correct and which one is wrong? Well, the first one I did was subtraction first and then multiplication. Multiplication first on this side and then subtraction. So clearly this one's correct, which means I need to make sure that it's clear to you that that right there was the wrong answer. The correct answer up here would have been a -5. Now let's discuss formulas and mathematical models. An equation is formed when an equal sign is placed between two algebraic expressions. For example, if I had x squared plus 2x equals 6x minus 1. Notice by itself, x squared plus 2x is an expression. By itself, 6x minus 1 is an expression. But when you put an equal sign in there, it becomes an equation. Okay? Now, a formula is a special type of equation that uses letters to represent a relationship between two or more variables. And usually that's in the context of having some real-world application. So like c equals 5 over 9 times f minus 32. This is an example of a formula. This converts Fahrenheit degree measurements to Celsius. So we could use this type of formula to plug in a Fahrenheit value and figure out what the corresponding Celsius temperature is. Another example you see here that I've got is a formula for modeling a gray wolf population. This formula, P is equal to 0.72x squared plus 9.4x plus 783, models the gray wolf population in the United States, X years after 1960. We are asked to find the population in the year 2000. Okay, again, we got to make sure we understand the model. This is the formula we're going to plug into, but X represents number of years after 1960. If we want to find it in 2000, what will X be? Well, I'll take 2000 minus 1960 to figure out how many years have gone by. Clearly that's 40, so I'm going to let x equal 40. And then I plug that into this formula everywhere there's an x. P is equal to 0.72 times 40 squared plus 9.4 times 40 plus 783. Using order of operations, I will first do the exponent, so I have 0.72 times 40 squared, which is 1,600, plus 9.4 times 40, plus 783. Now I can perform my multiplications. So going across here, I take 0.72 times 1,600 in my calculator, I get 1,152. If I take 9.4 times 40, I get 376 plus 783. If I add those numbers up in my calculator, I came up with 2,311. Okay? Now, because it's a word problem, I need to interpret my answer, 2,311. What? Gray wolves is the units that we're talking about in this particular example. The set of real numbers. Let's begin by talking about what a set actually is. A set, by definition, is going to be any collection of objects whose contents can be clearly determined. In mathematics, we most commonly talk about sets of numbers, although we can talk about other types of sets as well. Consider the following set. I put a curly brace and then let's say 1, 2, 3, 4, and so on. That's one way of describing a particular set. Now, you should be able to tell what I mean by this set by the way that I write it. In general, in mathematics, we will always use curly braces to represent or denote that we're talking about a set. And inside the curly braces, I will describe that set. In this particular example, I used what's called the roster form to indicate a set. This set, 1, 2, 3, 4, and so on, is described by listing the values, much like a class roster would list the students in a particular class. I also want you to note the ... here. That's called an ellipsis in say, grammar. What that means is continue on following the same pattern. Right? So 1, 2, 3, 4 has established a pattern. So every number that fits into that pattern is also in this set. This would be an infinite set. So the number 7 is in this set. Even though you don't see it here, it fits into the pattern. 27 is in this set. 1,000,000 is in this set. Okay? Now let's talk about some of the most common sets that we work with in mathematics. One set is the natural numbers. That's the most basic of all sets. It is the set 1, 2, 3, 4, 5, 6, and so on. It's the same set I just wrote up here as an example. Notice it starts at 1 and begins the counting. It's counting numbers. It's the first numbers we learn whenever we're children, right? Because we begin counting on our fingers. Well, the next set is actually not that different from natural numbers, but it does add one more element that is important to consider in many contexts. It's 0, 1, 2, 3, 4, 5, 6, and so on. The number 0, which is not considered a counting number, is what's called a whole number. And that's the only distinction between those two sets. Sometimes we're talking about the numbers that start at 1. Sometimes we're talking about the numbers that start at 0. The next most common set to be used is the set of integers. Now, integers include all the natural numbers, all the whole numbers, but also negative numbers as well. And the way that I would write out the set that has all of these, 0, 1, 2, 3, and so on, as well as the negative numbers, I'm going to write them out to the left. -1, -2, -3, and so on out in that direction. Okay? That infinite set, which appears to be infinite in both directions, right, is the set of integers. It's all positive and negative natural numbers and 0. Okay? Now, in many cases, to describe sets beyond these types of numbers, we need another type of set notation called set builder notation. Instead of listing the numbers inside a set, we want to just describe some property that those numbers have. And the way that we do that is using the following. We would write a curly brace, a variable, a vertical line, and then the description of that variable. In this case, I have written the set of all x, and the vertical bar is read as such that. So the set of all x such that x is a natural number less than 6. We have described our set using set builder notation. Now this is a particular example where we have described the set that could actually be described by roster form, right? What set of numbers is this? What is a natural number and less than 6? Clearly those are the numbers 1, 2, 3, 4, and 5, and it stops. It does not go on forever. So this is a finite set of numbers. Another important notation that we use when talking about sets is the element of notation. This symbol that looks like a C with a line through it, also looks a lot like the Greek lowercase epsilon, is read is an element of. Okay, so for example, 7 is an element of the set 1, 2, 3, 4, and so on. Right? It is in that set. Now, to describe something that's not in the set, we would use the element of, but put a line through it. So that would mean is not an element of. So, for example, 1/2 is not an element of the natural numbers. So what types of numbers have fractions, right? So far we've considered positive and negative whole numbers, or the set of integers. What about numbers that have fractions? What type of numbers are those? Well, in mathematics we refer to those as rational numbers. When you see the phrase or the term rational in mathematics, you almost always think fraction. I can write, sorry, rational, think, fraction. Okay, so the rational numbers are the set of all numbers that can be written as a fraction. In other words, a over b, where a and b are integers and b is not equal to 0. We'll come back to why b can't be 0 in the next section. So numbers like 1/4, negative 2/3, the number 5, right? Even though it doesn't look like a fraction, realize it can be written as 5/1. Right? So that is an integer over an integer, which makes all whole numbers, in fact all integers, are also rational numbers. There's also a set of numbers that are called irrational. What that would mean is something that's a number that have a decimal representation, but that decimal representation doesn't terminate or repeat. Okay, and there are a few numbers out there like that. Numbers like, say, the square root of 2. If you plug the square root of 2 into your calculator, you will get something like 1.414213562237. And that's as far as my calculator goes, but in reality that number goes on forever. That decimal expansion does. Okay? Square root of 3 works the same way. In fact, any radical of a non-perfect square, any square root of a non-perfect square, is going to be irrational. There are other numbers in mathematics that you may be familiar with. If not, we'll come back and talk about them a little bit later. But numbers like pi, right? Pi is that number that is the ratio of any circle's circumference to its diameter. Okay, it's a very specific number, but it's about 3.1415926 and so on. Okay, it's a very specific number whose decimal expansion does not repeat and does not terminate. It goes on forever. That's an irrational number. The last set that we're interested in talking about in this section is the big set for us. It's going to be the set of real numbers. Now, a good enough definition for this class is to say that those are any numbers that are either rational or irrational. Any number with a decimal expansion is a good enough definition. And if you think of all the sets that we've talked about so far, here's kind of a breakdown of what those numbers look like. Right? We start with natural numbers and we keep making our set bigger. So natural numbers, whole numbers, integers, rational numbers, they were each contained in the next set, except rational and irrational are two distinct sets, but if you put them together in one big set, you have a real number. The real number line is a graph that is used to represent real numbers. The origin is labeled 0. And a unit distance is marked out repeatedly in each direction to indicate the integer positions on the line. So we start with 0 and our positive numbers go to the right and our negative numbers extend out to the left. Okay, so this is what the real number line looks like. The real numbers are points on the number line. We use the number line to graph single real numbers or sets of real numbers. So for example, you can see on this graph here, we've got a dot on the number 3, 0, and 4. That is a graphical representation of the set -3, 0, and 4. We graph them as dots. Something that we will do later on is shade regions of the graph of the real number line to indicate intervals of real numbers. But another thing that we can do with the real number line is talk about the ordering of real numbers, meaning which numbers are bigger than other numbers. Using inequality symbols, we can indicate which numbers are bigger or less than other numbers. This symbol, x is less than y, indicates that the position of x is to the left of y on the real number line, by which we mean that x is smaller or less than y, right? So the smaller end of the little less than sign goes on the smaller variable or the smaller value. On the other hand, if you switch that over and say u is greater than v, that means that the value of u is to the right of v on the real number line. One modification that we sometimes make to those symbols is to put a little bar underneath them, as you see in these two examples right here, or these two lines here. That means that it includes the equality value. So this symbol means less than or equal to, and this symbol means greater than or equal to. So let's use what we know now to determine what each of the following inequalities in examples A through D mean. So write out the meaning of each inequality and then determine if it is true or false. Remember that we read from left to right. So in this case, this is saying that -8 is less than -2. Now, is that true or false? -8 is to the left of -2, so it is less than, which means that's a true statement. Even though the number itself, 8, if you ignore the sign, is bigger than 2, when you put the negatives on there, it makes it true that -8 is actually less than -2. 7 is greater than -3, which is also clearly true because 7, which would be over here to the right of -2, means that 7 is greater than -3. Okay, this one is read as 5 is greater than or equal to 5. Now, is that true? Well, it's not greater than, but it is equal to, and all you have to have is that one or the other of those is both. So greater than or equal to is true, because they are in fact equal. Is 2 less, let me try to write that better, is 2 is less than negative 14, less than or equal to, actually. True or false? Well, that's clearly false, because in order for it to be less than or equal to, 2 would have to be left of negative 14, and 2 is here, negative 14 is way down to the left, so it is not true. In other words, it's false. Okay? Now with that, we are done with section 1.1, and we'll be ready to start 1.2, where we cover the operations and properties of those operations on real numbers.